Okay. I'm not seeing myself, but I hope it's fine. I hope everyone else is seeing me. And we have another problem today. Let me set a 20-minute timer. It's also a hard one. I'm only solving hards now, or like suffering. Actually, the yesterday one, I spent like 30 minutes more to solve it in 2 different ways. But that was off screen. Okay, so we are giving an integer array nums, list of integers, and k, which is an integer. Split nums into k non-empty subarrays such that the largest sum of any subarray is minimized. Return the minimized largest sum of the split. Subarray is a contiguous part of the array. Okay, so we are returning integer. What I don't understand yet is what is the largest sum of any subarray. So is the largest sum a sum of any two numbers in this array, subarray? What if there is just one number? So I will need to see an example. Okay, so there are 4 ways to split the nums into 2 subarrays. That's correct. Yeah. So because it's not empty, okay, the best way is to split into 7 to 5 and 10 8, and where the largest sum among the 2 subarrays is only 18. Okay, largest sum is we are summing all numbers in the array, I'm guessing. Actually, still am not getting this. Because we don't have an example of an array where we have like with the largest sum of 3 elements. Okay, actually here 7 plus 2 plus 5, yes. Largest sum of elements in the subarray, or largest sum between any 2 elements in the subarray. Okay, since there can be an array with 1 element and then it's unclear what is the largest sum, so we will just be assuming that it's a sum of all elements in the subarray. Okay, so let's do first a simple example 1 2 3 4 5, and k will be equal to 2 at first. So 2 at first we already know it's 9, and essentially we are trying to draw a boundary between these arrays, right? So we are drawing the boundary here, because if we move 4 to the left, then the left sum will become 10, which is bigger than it currently is. Okay, so when we have a split of into arrays, the solution is kind of trivial, but let me just share it so that we can maybe build upon it later on. So the solution will be in case of k equal 2, calculate prefix sums, and then choose the one that minimizes the sum. Choose the one break that minimizes the sum of subarrays. So that's the idea basically. One thing that I want to highlight is that we are never told that it's always positive subarrays. It's just that they're contiguous. So It can easily be something like this. Let's just see how this goes then. Yeah, here we will still have to like look through all the elements of the arrays. So what is the problem? The problem is that we don't know what is the sum that we are targeting. So okay, let's look at it first. So here we would probably want to do okay -1. Then if it's -1, then in this subarray it's -3 and -5, -8 +6 -2. Yeah, I think it's like -1, because if we start doing that, then we get 2 at least. If we start doing that, when we have -1 again, and on the left we have, yeah, at least -1 already, right? And then if we do that, we get at least 2. So yeah, but I had to iterate through the whole combination of arrays to reason about that. So now let's do something more complex. Let's say that we need to split it into 3 subarrays. Then I think it will be 5, because we definitely don't want to... Oh, it's not 5, right? It's 6. So if we have to have 5 as one of the subarrays, then the question becomes how to split this subarray that is left in 2 parts. I'm thinking in the direction of dynamic programming, and I'm also thinking in the direction of binary search. I will now try to cover both of those cases, right? So why am I thinking in the direction of binary search? Oh, sorry, dynamic programming first. It looks like there is a repeatable pattern, right? So, for example, we try to put, we have many possible positions to put one of those borders. And then first, we, depending on the index at which we are putting this like separator, we already, let's assume, memorize the calculation for the subarrays between like I and j. So we have a state of between I and j, like I, j, and k. Yeah, so it's like 3-dimensional dynamic programming. So if we have ij, let's say everything between index, how should we call these indexes, right? So this will be 0, and this will be length of the array, which is 5. So everything between 3 and 5 will be left inclusive, right non-inclusive, right? And we, if we don't need to split it, so it's like 1 subpiece. If we need to split it in 2 pieces, if we need to split it in 3 pieces, however many pieces do we need. And then, yeah, then it is just an iterative approach where we memorize the state as I, j, and k. So I, j, k, minimum sum that you can get from splitting an array between I, j. What minimum largest sum that you can get from splitting this array k ways, right? So the problem is that here, let's calculate our running time complexity, right? Yeah, that's why I'm thinking in the direction of binary search. I will get to it in a moment. But here for each of those options, we have, yeah, so essentially it will be O of n squared times k solution. Because we need to try all the combinations between ij, and for k up to n, it will be the amount of space and the amount of runtime, because we need to calculate each at least one. So this is one of the possible solutions. Then let me mention the binary search and why I'm thinking in this direction. So if we have a specific largest sum that we are targeting, then we can try to just calculate whether we can achieve this largest sum of the subarrays in k subarrays. How do we do that? Let's say we define 6. Oh, okay, let's say we define first, I don't know, 20. Like the whole sum of this array, what will it be? It will be 15, right? So this is the biggest possible thing that we can get. So 15 is, or maybe we should do something else. Okay, let's do 15. 15 and 1 are the two possible boundaries, right? So let's say we try something in between. Let's say it's 7 or 8. And what we do, we start from the start of the array and we add elements one by one until we get to the end of, like until we cannot add any more elements, so that it's still below this sum. So here we will first add 1, 2, 3. Adding 4 will bring it to 10, which is bigger than 8. So we cannot do that. Then it will be 4. So 4 is valid. 5 is valid. We cannot add 5, so it will be, what I'm saying is valid, right? Let me rephrase that. So we first add 1, 2, and 3. It becomes 6. We need to create a new subarray. We add 4. We cannot add 5 because it will be 9, which is bigger than 8. So we only add 4. And then we add 5 to the third subarray, and we see that we were able to add all the numbers and 3 non-empty subarrays, such that for each of those, the sum is lower than a specific number, which is 8 in this case. So 8 now becomes our highest boundary, and 1 still stays our lowest boundary. Then between 1 and 8, divided by 2, let's say it's 4, right? So then when we try 4, we add 1 and 2, then we add 3, and then we add 4, and we still have elements left in the array. And because of that, we can say that, okay, 4 is too small a number. So then if we do such a binary search between like the biggest and smallest border, then we have how many steps to take. Okay, so it will be O n on each step. So checking whether we can make this size of the array valid, like this split valid for this particular target sum. We have to spend n operations on that because we will try to iterate through the whole array. And the how many operations do we need? How many such operations do we need in total? It will be on the order of log of sum of n, sum of the array. Okay. So this log of sum of elements, we don't know if it's big enough, but if it's small enough, if it's a reasonable thing. So both solutions might be better depending on whether n times k is bigger or smaller than the number of elements. But I think the second one is cleaner, the binary search solution, so I will be implementing this one. Implementation. Okay. Now, for nums, let's first define a subfunction which is def split is valid. and we will be just using nums from the outer scope, but we need to have key. Key doesn't change, it will be from the outer scope, but target largest sum. Okay, so we have total subarrays, which is starting with 0. We have current subarray sum, which is equal to 0. And then for num in nums, oh damn, is it actually working? Yes, I think it's working. What I was worried about now was that binary search only works for the positive numbers, and I remember that we can have negative numbers, but these two things are unrelated. But it does create a problem for us, doesn't it? Or it doesn't? No, it doesn't. We always can add the next number and check if it overflows the array. If its number is negative, then it basically helps us a little bit. So yeah, it sounds reasonable. But that means I was saying that we need to calculate the possible target sums between the sum of the array. I think we need to calculate it between the sum of all positive numbers and sum of all negative numbers. So this will be our two borders for the possible target sums that we can theoretically achieve. Largest sums. Maybe also let me just mention another corner case. Let's say it's the same one as here, but let's say we need to split into 6 ways. And in this case, it's impossible. So I will just assume that we will never get such a case where we have bigger k than the number of elements in our array. Okay, so for number in numbers, current subarray sum, if current subarray sum plus num is bigger than target largest sum. So what do we do then? Then we do total subarrays plus or equal to 1, and then current subarray sum will be equal to num. Else current subarray sum plus or equal to 1. Why I made a pause here is because I want to understand what do we do. Like, we are never adding the last subarray in the count of total subarrays in this way. So let's say we added the first 3, and then we added this one, and we can add the next one, so we add it yet another time. And then do we always have a non-empty subarray in the end? Yes, we always have a non-empty subarray in the end, because we are always adding at least one number to it on each of the iterations, and by the end of this loop, its invariant is that the total this current subarray is non-empty. So we might as well start with total subarrays as 1. It's a little bit non-clean. 1 So this is just for readability. Okay, now we need to write binary search. We have spent 20 minutes on this problem. Let's continue. Left will be equal to sum of num for num in nums if num is smaller than 0. And right for bigger or equal to 0. Then I need to reason a little bit about our array and what we need to return. So what we want to do is we have this array, let's say we need to split it into 3 parts. So then we will have target sums between 1 and up to 15. So I want to find a sum such that my right pointer is pointing, okay, somewhere in the middle. We know the right answer will be 6. So my left pointer will be pointing to 5. Let's put it this way, 5. And 6 will be pointing to the right. So basically, the invariant for this binary search will be that the right pointer is always pointing to the sum value that is valid, and L pointer is always pointing to something that is invalid. Since 1 can theoretically be valid, then we need to do it -1. So now we make it invalid so that the invariant stands correctly. And then what we need to do is we need to do the binary search. So while L plus 1 is smaller than R, so while they are not on the closest 2 points to each other, what do? We calculate middle as left plus right minus left divided by 2. And then what we need to do is, if split is valid for this candidate sum, if split is valid for candidate sum, so split is valid, then it means that we can confidently move right pointer to this, because we're always, right pointer is always pointing to the valid sum. So valid right is candidate sum. Else, so it's invalid. I have never returned anything from here, right? Yep. So if return, and what do we need to return? Total subarrays is bigger, smaller, or equal to. Okay, so it can be smaller, right? We can actually be able to get the target sum. Let's say we have 15 and we try 15. We can get to 15 by just counting all the numbers. It means, given that we never have these situations, we can always, if we can achieve sum of 6, then sum of 15 is always also working, also valid. So if it's smaller or equal to k, then we return true. Otherwise, we return false. Okay, so now if it's invalid, we can confidently put L as candidate sum, and then finally we return R. Okay. Okay, I wanted to copy this, but let me first actually try this thing and try to check if it works. So I want to split this in 3 possible subarrays. We start here. So okay, sum of the empty array. I will assume that this just returns 0, so it will be -1 here. And then here, sum of the possible positive nums will be 15. Then, let me create pointers. Oh no, pointers. I need to create pointers for a different thing. I need to create pointers for left and right. I will not be creating pointers for all of those things. Let me just do like -1, 15. Okay, so this will be left and this will be right. Cool. Now let's check. So first, L plus 1 is smaller than R, yes. So candidate sum will be R minus L 16, okay, basically 15 minus 1 divided by 2, which is 7. So if split is valid, candidate sum, let's check. First we check with 7. And we iterate over the number in numbers. So let's see what will it be. It starts at 1. But then we will be updating this. This starts at 0. We will be updating this for num and nums. Like 1, we're adding it here. Current subarray sum plus num, 0 plus 1. No, it's not bigger than 7, so we make it 1. And going here. And then we iterate on the next loop. So now 2 is still not bigger, so it becomes 3. Going into this branch, we go back here. Adding 2, no, it's still... Oh, so adding 3, sorry, so 6, still smaller than 7. So we go through this branch and then go back here, and finally we get to 4. As we get to 4, this becomes 10. It would have become 10, but we catch this situation and we say, okay, now we are iterating to the new one. And the current subarray sum becomes equal to the current number that we are considering, which is 4. Okay, so now we get to 5. And again, 9 is bigger than 7, so we make it 5 and we make it 3. And we return total subarrays smaller than k. Yes, it's 3, which is valid. We need to split in 3 parts, so we know that 7 is valid. So now our right pointer start pointing to 7. Okay, now we are iterating once more. And here we are considering number, which one? 7 minus 1 divided by 3, or divided by 2, which is 3. So we are considering 3. And the total subarrays is 1, and the current subarray sum is 0. So if we add 1, no, it's fine. If we add 2, no, it's fine. It's exactly what we need. Once we add 3, it's not fine. Then it becomes 2, and it becomes 3. Again, we cannot add. So, oh yeah. There is a corner case that I'm not sure I'm processing right now. What if our number is bigger than the whole target that we want to cover? Yeah, it will be returning possibly a valid thing when it's actually invalid. So if num is bigger than target plus sum, we can just confidently return false. Otherwise, yes, otherwise we need to continue iterating here. Okay, that's good. We have caught one error in our analysis. So now we are getting to 4, and 4 is bigger than 3, so it's definitely invalid. We are returning false. And here we now make L equal to 3. So, sorry, minus 1 and 3, and R is pointing to 7, L is pointing to 3. Fine. Let's now try 3 plus 7, 5. Can it be 5? So candidate sum is 5. We are going to 5 here. And we are adding numbers like 1 is fine, 2 is fine, it's 3. We're adding 3 and no, it's not fine, so this is becoming 2. And this becomes 3 again. Then we try to add 4. This is not fine. We are adding 4 and like, okay, essentially we have 4 subarrays in the end, and we don't have this number of subarrays that is smaller, so we know 5 is also invalid. And L is now pointing to invalid 5. And finally, we have 5 plus 7 divided by 2, which is 6. We already know that 6 is valid. So here we're considering 6. So once 6 is valid, we make R pointing to 6. And this means that now we get out of this loop and we're returning 6. Okay. A last check. I need to check that just to ensure that all my tests are considered. Yes, we did consider negative numbers. They won't change things much. Then another thing that should be considered, yeah, here maybe we should, it might be bigger. It's basically sum of absolute of all the elements. This will be our running time. Maybe we should also mention the space complexity, and it will be just this because of all the recursive calls that we are making, but we are not storing anything else anywhere. And then I should check what we are returning. Yes, we are returning things here always, something from this function. There is another return. And here we're also always returning. We don't have any methods defined, so I think basic errors are checked for. This works, and this also works. Okay, great. We have solved a hard problem pretty cleanly in 32 minutes. I guess this is good. Let me now check what's written in the chat. Sorry, I wasn't following it too much. You code in assembly. Oh, the owner of bread. What's your favorite language? My favorite language is assembly. Hello, do you read the messages? Yes, I actually do, but sorry, I was focusing on the solving of the problem, so I wasn't reading all the messages. There was another person asking whether they code in assembly. Yeah. I have never, okay, I did code in assembly. I passed one course. It's actually a very good one. I recommend it, from NAND to Tetris on Coursera. And there you build the computer from scratch, and as part of it, you're writing code in assembly. But that was my only exposure to assembly. I really like Python, as you can see, and I'm a machine learning engineer, so Python is my main language. I did code in a few more, but my main language is Python. Yeah. Okay. Cool, guys. Yes, definitely coding in assembly is a very specific thing. What else I do know about assembly is, if you compare developer productiveness in solving specific problems, then whatever language you use, it's mostly the difference is insignificant, on average, because for shorter projects, probably Python is easier. For bigger projects, strongly typed languages are better suited, but assembly is just slow. So if you compare programmers choosing the same problem with different languages, then on average, assembly will be systematically slower. Everything else will be not. So is coding and assembly demanded skill in tech? No, it's not. Is LeetCoding a demanded skill in tech? No, it's also not, as you probably have heard about already online. People will always be saying that LeetCode is not needed, which is kind of correct. You might never use LeetCode. It's always not about LeetCode, and that's not what I'm doing here. I'm not trying to solve LeetCode, guys. I could have done that without streaming. I am learning to communicate while I'm solving the problems, and this is the big part. Like, if you looked at me solving this problem, would you want to work with me? That's the question that interviewers are asking. How can I explain my reasoning? Yes, being able to solve the lead code is important. If I'm just stuck and I cannot unstuck myself, or if I just look stupid, obviously people wouldn't want to work with me. But coding by itself is just part of the coding, and the bigger part of it is a behavioral interview. And am I an engineer? Yes, I am a machine learning engineer right now. I work for Turing.com. But yeah, I think I need to go. Thanks everyone for watching this today. I will return tomorrow, and thank you all.